Since very early, we are taught that matter is made of tiny building blocks known as atoms. However, these are not the most fundamental particles. The electron orbiting around the proton is, as far as we know today, fundamental. This perpetual motion is kept by the electromagnetic force, mediated by the particle of light, the photon. Protons and neutrons reveal their complexity as they are made of quarks, in the case of the proton, 2 up and 1 down quark, which are glued together by the strong force, mediated by the gluons. If this were the whole story, our universe would not be as we observe it. Take beta decay for instance, where a neutron in a heavy nucleus transforms into a proton by sending out an electron and a neutrino. A closer examination of this process reveals that these particles don't interact directly. Instead, this process occurs via the exchange of another force carrier, the W boson, and this weak interaction would not be complete without the Z boson. Over the past century, 3 generations of quarks and leptons have been discovered. Though very similar, these particles differ in mass. However, for the laws of physics to make sense, there must be something missing here. In a universe with only quarks, leptons, and force carriers, there is no elementary mass. So, where does this mass come from? To understand the origin of mass, we must introduce the Higgs field, phi. It turns out nature's ground state is governed by the Higgs potential. However, having the potential minimum at the origin does not solve the problem of mass. So, the parameters must be such that the field is non-vanishing at the lowest value of the potential. And, as nature prefers stability, everything must happen around the ground state, or, in other words, the vacuum. Via this dynamical process, which is called spontaneous symmetry breaking, all elementary particles gain mass, except for neutrinos, gluons, and photons. But this is not the full story. Just as with the electromagnetic field, the Higgs field has its own physical manifestation, the famous Higgs boson. This full picture where particles interact with force carriers and gain mass through the Higgs field is known as the standard model of particle physics. However, it is still incomplete. In my work, I will investigate possible solutions to questions unanswered by this theory. For example, the 3 generations of neutrinos oscillate amongst themselves, and this implies that they are massive particles, contrarily to what is predicted by the standard model. Moreover, the standard model falls short in explaining the specific values for the observed fermion masses. Why is the electron much lighter than the muon? Why is the top quark the heaviest one? We also don't know why quarks and leptons from different families mix the way they do. All these problems make up what is called the Flavour puzzle. My proposal to solve the Flavour puzzle is based on extending the standard model by adding another copy of the Higgs field. In this Two-Higgs-Doublet model, there will be new Higgs bosons. I will also assign a new kind of charge to each fermion and Higgs field, which I call Flavour charge. In this new theory, neutrinos acquire their mass from effective interactions, which appear as a result of considering the standard model as an effective theory, which stems from a more complete framework valid at higher energy levels. All these ingredients together make up the minimal U1 to Higgs doublet model for quark and lepton flavor.